Thank you very much. So let me start. Maybe before we'll go to the main part of the presentation, a small disclaimer. The presented work disseminates results of my own activities, which were done using solely owned private resources. Therefore, the opinions and views presented in this talk may not necessarily express the opinion and views and policy of my employer. And also, examples which you'll see in this talk are for demonstration purposes and do not necessarily reflect the real-world product. Okay, so the main question of today's talk is, can we trust integrated circuits and silicon chips? And to answer this question, we must answer another question, namely, do we have a choice? Because due to the technological barriers, high production costs, we must count on manufacturers' honesty and popularity. And there are whole countries which don't have own silicon production. So, also there are many organizations and companies which must buy integrated circuits because they cannot afford production. So what they are doing is they commonly use high volume products from leading manufacturers, counting on the honesty, on the fact that due to the popularity of those circuits, it will be easier to detect threats and the consequences will be severe. This is possible in the mainframe computing. In telecommunication, it's more difficult, and it's very difficult in the embedded world, especially Internet of Things, where you have a lot of small manufacturers. So already this approach, buying from a big producer, is not available to everyone. And then, but comes the question, is there a reason for a concern? Is equipment from a large supplier safe? And what is the threat? What it can do, actually, if we'll have such a hardware Trojan? So is it worth to get a closer look? So this presentation is thought as an introduction to the domain, assuming that you have mainly a software background. So it will show you, actually, the topics, the introduction, what can be done, rather than how it precisely is done, to give you a broad overview. Okay, so before we start, just to check that we are on the same page, what is a hardware Trojan? Hardware Trojan is a function of a hardware component hidden from the user, which can add, remove, or modify the functionality of hardware component, and therefore reduce its reliability or create a potential threat. So here we have a simple signal, which is an inverter. And in order to introduce in this circuit a hardware Trojan in integrated circuit, we would have to firstly do the payload modification, which means that we are modifying the circuit. Here we are adding AND gate. And next we are adding a trigger. So it's a signal activating the payload. Triggers can be combinational, sequential, as you want, but all in all, it's modifying the signal which is going to inverter, and we can get different results than we thought we'll get. So what are the similarities to software Trojans? First of all, its intention. It's infiltration, exfiltration. So either to get the data out of the company, either to allow easier attack, and also their designers would like to hide this functionality from other users, so it's seldom activation. However, there are very strong differences. First of all, hardware Trojans in integrated circuits cannot be removed post-deployment. So the possibilities of updates of circuits are very limited. You have micro-coded machines, but this is definitely very expensive and very limited approach. Later on, those Trojans do not spread. They must be manufactured, which means either you have an equipment which has a hardware Trojan, either you don't. And once you have it, once it's on the market, it will be always there. You cannot remove it with an update, so manufacturer has a problem. And then we have high production costs in terms of equipment and skilled labor, but understood as an amount of money which you need to train these people. So don't forget also about the most popular option where we have, it's still the hardware-software co-design. So some parts of such a Trojan are done in hardware, some are done in software. So just a brief review of the history. The history of hardware Trojan started in 2005 with this famous report from Department of Defense. which claim that there is a possibility of modification of integrated circuit in the fab, in the silicon fabrication unit. So it's at the very end of the chain. And here is the number of publications with two words, Hardware Trojans in Google Scholar. As you may see, it's skyrocketing. In between, we've got Snowden affair in 2014, which showed that actually there are big organizations and institutions like NSA, which are very interested in this kind of threats. So we have last year more than 2,600 publications concerning hardware Trojans. So it's a definitely hot topic. So maybe this is the first reason to get a look on it. Those 2,500 publications has proven actually that there is a wide variety of possible Trojan deployments. So you may have different size. You can modify transistors, wires. They can be big. You can modify whole IPs, gates. They can be tightly distributed on a chip, so in the same place. They can be spread along the chip in different places to make it harder to find them. They may modify the layout, but they do not necessarily have to. Same with trigger. So activation, they can be externally activated through some radio connection, or they can be internally activated. So by set of conditions, it can be sensor data, if a chip has sensors, or logic, internal state, clock counter, some input instruction. So where we go from here? In order to give you a hands-on experience to see how complicated such a modification of integrated circuit can be, we'll start with a CPU example with a live demo. And later on, I will talk about where and when can such a modification be introduced in the process of the chip manufacturing. And finally, we'll talk briefly about methods and of defense, of detection, and their costs. So just a brief review. I'm sure that you all know, but all our software security is based on one basic assumption, namely that the operation of an underlying processor and its hardware is predefined and is working according to a strict specification and a set of predefined rules. So commonly applied is protection domains, which were introduced in 70s already. So it's 50 years in Multics, which is predecessor of Unix. So we have at least two modes of processor work. It's hypervisor and user, or kernel and user mode. In hypervisor mode, kernel has access to all commands and addresses. In user mode, it has only access to a subset of commands and addresses. And the transition between those modes can happen only according to a predefined and strictly defined set of rules. Syscalls, interrupts, and the holy grail of the majority of exploits is to get into the kernel mode to have an access to whole space. So I will show you an example of Spark architecture, how it's defined in the manuals. So you've got privileged commands, which can be assembly commands, which can be only executed in the hypervisor mode when the processor is in hypervisor mode. You have here in the Spark case a supervisor mode and user mode defined already in the manual. And here you have an excerpt from instruction set architecture where some commands have a small cross next to it, which means they are privileged. And I selected two of you. This is, maybe you can see them, but this is read processor state register and write processor state register. This register contains the information in which mode the processor actually is. And both commands are available only in supervisor mode, which means that the user cannot change the value of this register. When he's in the user mode, it must go through this hardware-software co-design procedure of switching the modes. So then, in order to explain how this security mechanism, which we would like to leverage, is implemented, we have to review very briefly how processor is processing the commands. Usually, we have this RISC pipeline, a pipeline with 5 stages of command processing. It's instruction fetch, instruction decode, execute, memory, and write back. They have a counterparts in data path. They are using instruction memory, register, ALU unit, data memory, and registers once again. And moreover, we have a pipeline, which means that all the stages are executed at the same time, but for different instructions. So then when we are implementing this hardware security mechanism, on each stage, what happens, so each stage has a different instruction. But what we are doing is, actually, this is a big while loop done in hardware, where we are firstly trying to decode the address of instruction from instruction memory. And if we see that processor is in the wrong state, we have an exception. We have a trap interrupt. The same, if we are decoding the opcode of the instruction, we are checking in hardware, this is a big if realized with transistors, if this instruction is legal, if this instruction is available in this mode of the processor, and so on and so forth. So here you see an example from Leon Free Spark Processor open source VHDL implementation. And here you see that we have some instructions which are available in user mode, and then you have here they are decoding the opcode. So when the instruction is in the user mode, they are not doing anything. But when we have instruction which is privileged, they are checking if the processor is in the correct mode, and if it's not in the correct mode, you have trap. So when we would like to implement a Trojan, what would be our payload? In this case, we would like to change the value of processor state register and switch to the hypervisor mode. However, the trigger should be available in the user mode. So this should be selected assembly command, which is available in the user mode, and with selected operand. So it can be add, which is giving us the result 878787. This is for the sake of simplicity of this talk. So here we have example of hardware software code design. So there is a software code which is triggering a payload done in hardware. So this is a payload which was published in my article from the Pwning conference. It's a fragment of the ALU unit. As you see, ALU unit has an access to the special register types, so also the control register. It's very simple. It's only three-liner. We are just checking what was the result of the addition done by the ALU unit, and we are changing the state of the register. So as you see, those are 3 lines of VHDL code, which will translate to a very small circuit. It will be, it won't change the size of the chip. And all in all, it's leveraging, it's switching the mode of the processor work. So now, if you would like to test for yourself how such a hardware Trojan is working, what it can do to your equipment, comes the question, do you need a silicon fabrication unit? No, probably not. Actually, if you can emulate a processor which is working correctly, you can also emulate a processor or integrated circuit which has a backdoor inside. So for the purpose of this presentation, I will use Camel emulator for the Spark architecture. The code is compatible with the VHDL code from the Geisler. I will use a regular Linux kernel in version 4.11, so it's fairly new. And the implementation and details of the implementation sources you can find on my GitHub page. So in Camel, you have this translate file, which is basically going through all instructions from ISA, which instruction set architecture, which we are trying to emulate. And it's translating them to the, in this case, x86 instructions. So here we have a read processor state register instruction. And we know that it's privileged. So here the first thing which Camel is doing is checking what's the mode of work of the processor. And if not, it's rising a trap. So then when we'll try to add a Trojan payload, we'll do this in the sign divide assembly instruction. And we'll simply put those couple of lines, it's also a 3-liner, where we are, whenever we are doing sign divide with this operands, we are changing the state of the processor register. So it's very simple. That's the point. So let me show you how does it work. So here, it's firstly we'll just run this. Oops. Let me. Okay. Okay, now it's better. So this is regular application. What we are doing here is we are doing a regular division. 1024 is 63, so we are not activating our Trojan. we have an inline assembly, which is right now commented, but I will uncomment it later. So we are printing the result, and we are doing something stupid. We are not very good programmers, so we are doing the null pointer dereference. So I have here a running Linux kernel. And then here's the output. So what we have here, we have a segmentation fault as it was supposed to be. So later on, what we'll do is, firstly, I will uncomment this line. So while being in the user mode, I will try to execute a privilege instruction. I will recompile the code. So, oops. I will copy it to the unit, to our virtual machine, and let us run it once again. So right now we have this trap. It's illegal instruction. We are trying to do something which is illegal. So right now we'll run the same code, but a bit different. What we are doing here is we are changing this second operand to 64. Yes, yes. Oops. Oops. Okay. So the sources are available on my website. Let's do this afterwards. But what you have here basically is, what we'll do is we'll just do this division 1024 by 64. Then we'll just try to read with this inline assembly, try to read the PSR. Then we'll try to write again something to PSR, because if we're in kernel mode, we should be able to do this. Then I will check if the result of this operation stays the same. And if it stays the same, then I will print the PSR. And finally, we'll switch once again to the supervisor mode and do this dummy null pointer dereference. Okay, so first of all, what we see here is that the result of the division has not changed, so the whole operation was conducted in the background. Secondly, we could read the value of the PSR, so it switched really to the hypervisor mode and went back. So the 8th bit of the PSR register has other values, the 8th bit changed to the supervisor mode. And finally, because we are in the kernel mode, null pointer dereference cannot be handled properly, so it has crashed simply, but it shows that we have denial of service. And now comes the question: how would you log, and how would you detect that this crash at this moment of execution from the logs was caused by some functionality which was realized in the background in hardware? Oops. Okay. Good. So we've seen that it's not that difficult, that it's very simple modification of a circuit. So now comes the question where and when it can be introduced. So I will discuss it based on the stages of a of a chip design. So first we have a logic design. So this is a very high level when we are deciding what the functionality do, and we are only giving clues how it should be done, or how should it be translated to real circuits with capacitors and transistors. So it's usually done in a hardware description language. It can be Verilog, it can be System Verilog, it can be VHDL, as in this CPU example which we've seen. So the introduction of Trojan will be very similar to introduction of Trojan in a software. You're adding, as you've seen, a couple of lines. This is relatively cheap. However, because hardware cannot be changed in post-deployment, the hardware, you have a severe testing. 80% of the hardware design of cost of hardware design is caused by testing, which means that if we are creating this hardware Trojan at this stage, this code will be tested over and over. That's the biggest amount of the workers, the highest number of workers which are devoted to this phase. And it's very hard to keep it hidden from your own corporation even, or organization. So what you could do is you could do obfuscation. So you could create a code which is semantically correct but difficult to understand. Or you can, and it's obviously easier in bigger projects which have a severe backward compatibility, like x86 architecture, which has features which are necessary just to run code which is 50 years old. At the second stage, we have synthesis. So from this high-level description, we are getting the real circuits with capacitors and transistors. Right now, it can be the metaphor, the software metaphor would be a code compilation process. So right now, in majority of projects, the synthesis is done automatically using the tools. So here, the Trojan would be already introduced as a modification of electronic circuits. So you need new wires, new transistors, new capacitors. This is a low-level approach. There are reasons why people are compiling electrical circuits, because it's very costly and very complicated. And here you have two possibilities. Either you are working with compiled code, so with a compiled circuits, generated circuits, but then these are normally optimized and they are not prepared or not designed to be read by humans, or modification can happen during the compilation process. So during the synthesis process. So then comes the question: who is checking the code which compiler produces at the output? So here it's easier to hide because we have less developers involved and because we tend to trust our tools which we are using, but it requires qualified and experienced personnel, and this is costly. So it's not that easy, and still we can use the white box cryptography, so produce complicated layouts to hide the final functionality. And finally, we have mask design. So from the layouts, we are creating masks which will be used during the production of wafers. So we could, obviously, we could modify those masks, but we are not doing it by scratching with a scalpel the real masks. We are using it by creating a new set of masks. This happens at the far end of the design process. So this is a very hard to detect. It's a low abstraction level. It's extremely hard to detect. But you need very, very skilled personnel, expensive tool, know-how, and preferably market position. You have to have your own fabrication unit. And here is an important point. Each of those stages is done usually by a different entity within the organization, by a different subcontractor, different company. Which means whenever the layout is coming to the fab, usually they are not testing the functionality. If you want to print something out, people are usually not asking what you want to print. They are just telling you, okay, for printing, that will be the price. The same with integrated circuits. So the lower you are in the phases of the chip design, the harder it is actually to detect this malicious functionality. That's what Department of Defense wrote in their report. So what are methods of defense? Very briefly, we are working with the majority of us. It's using post-manufacturing Trojan detection. We are buying a chip, and we have to do something with it. We have to check it. So first of all, it's very difficult and expensive. It's not an easy task. The most straightforward approach is based on the golden chip principle. So we have to have an idea how a circuit should look like without the Trojan. If we have this idea, and I strongly, I want to say if we have this this possibility, then we have to firstly get the chip. Here is a very old epoxy case from 80s from Intel. There are several methods to achieve it. You can do it mechanically, or you can do it chemically, or both. However, it's difficult because preferably you want to take out this case and do not touch the chip. Even if you're doing it with acid, you don't want this acid. It's not every substance, because you don't want to modify the functioning of a chip. Why? Let me show you it here. Here we have a photo of a Z80 processor. It's a very old one, but this processors from 70s, 80s, maybe early 90s are the one which you can do as a hobbyist. They are in a very high or very old ancient silicon production technology, 1,500 nanometers or so. So if you are trying to read such a silicon, it's firstly you have to realize that it's highly optimized due to technical and economical reasons. So not all reasons are obvious. For instance, in the Z80 we have this register bank over there, and the register, according to the documentations, are 8-bit. However, the implementation is a 4-bit, which is working in 2 cycles. Why? In modern computers, it makes no sense, but at that time when this chip was designed, they made some other decisions, and they said, we don't want these registers to be single cycle access because other components of this chip are very slow. It's an economical decision. Then the chip works in parallel. So we all know that to debug the parallel code is very difficult, and here we would have to really stimulate those inputs which you have on the edges of the chip to see what's happening in the chip, to see what parts of the chip are active during which operation. And finally, we have legacy functions. So we have some parts of the chip which may not necessarily be directly connected with the basic functionality. So what we would do is we would cut each layer because it's a 3D design, and we would make a photo or scan it with electron microscope and compare it to this layout from the golden chip design. So the pro, it's a very high reliability of detection if you have a golden chip. The question is how you get a golden chip from leading manufacturers. They are not showing you their layout. You don't know how the i7 should look like or its main functionality. Same for telecommunication devices. Also, it's very expensive, time-consuming, and destroys the chip under analysis. So if you are ordering 100,000, for instance, integrated circuits or chips, and you are getting them, how percentage of them what's the percentage of them which you would like to sacrifice to check if they have a Trojan? If it's, I don't know, 1%, 2%, firstly, those are losses for your corporation. It will be very time-consuming because you have still a lot of chips to test. And finally, what about 98% which are left? You haven't tested them. And the last question is it enough? Is such an inspection which I showed you enough? To answer this question, look at this simple inverter. This is the example from the beginning of this talk. We have here, it's a very simple circuit. We have 2 transistors. Depending on the input signal, either one is open and another closed, or opposite way around. So this is giving you the simple inverter functionality. And here is the Trojan. Every one of you can answer the question in which of them is Trojan. The answer is, actually, you have to check what are the dopants inside of this gates, because this is how the gate will look like on the integrated circuit when you will make a photo. And then will appear then in the A circuit you have two different transistors, but in the B circuit you have a Trojan, because you have twice the same transistor, the circuit is always half open, and the signal is wrong. So optical inspection in this case is not enough. You have to go deeper. You have to check what's actually inside. So where it can be used, this is actually proposed to be used against cryptography or crypto engines, security units. Here's an example of AES based on an excellent PAR presentation from the last year, 2017, from Germany. In AES engine, you need a random input. You have 2 registers. First is random register, 32 bits, which should be random, but due to the aging, due to the temperature, they may not be that random as you would like them to be. So you have also counter register, which is just incrementing based on the number of operations, and you're using it to get the AES input for crypto key. So while doing the dopant Trojan, you could fix the number of the of random, really random registers or bits, or you could fix the variation between the bits in such a cipher. Obviously, the pro of this approach is you are not adding any additional wires or transistors, so optical inspection is not enough. The chip will look like a golden chip if you just look at and cut it into, slice it into pieces. However, obviously, the functionality of the chip is limited. So you have damaged chip parts, and you have, and functional testing, if you do the functional testing, it will find it right away. So this is a problem. What the producer could do is they could create anti-test function, as Volkswagen did with their car controllers. If someone is trying to test the crypto unit for all inputs to check if really it's using the full random space, it could just trick it and cheat it. And then finally, here comes the interesting question. If hardware components are so extensively tested because you cannot get rid of them once they're on the market, then what could happen is you could, as a malicious attacker, look for a very bizarre test cases, which are very rare and very complicated, and say, and leave them on purpose. So just to say later on, we all know that in software projects, people are saying it's not a bug, it's a feature. Here we would do this another way around. We would say it's not a feature, it's a bug, which is a very convenient excuse for manufacturers. I'm not saying that it happened, for instance, in case of Intel bugs. Maybe those are bugs. But such complex bugs could be used. And the manufacturer can also later on say, OK, this is a bug. We haven't seen it. We haven't tested it. Or it can say this chip is damaged. So we couldn't do anything in case of the dopant Trojans. So we haven't seen, our tests haven't seen or reported the damaged chip. OK, so let me wrap it up for you. So who should fear of hardware Trojans? I think everyone. Why? Because they are very difficult to detect, and they can leverage literally all software mechanisms, because you cannot build a trusted software on a not trusted hardware. So what can we do? I think we should build a skill first in hardware domain. So this is a personal training. So not having an industry branch of hardware, it's not a solution. We can see this. It's called balkanization of the electronic markets. Right now, certain companies are blocked in countries. So they are saying we are using only routers from our national production. This happened in the United States. This happened in Australia. This happened in Germany, in France. So if we have some kind of the low-level know-how, then we may start testing. The first thing would be to test the products. It won't prevent the attacks, but it will make them much more difficult. So once again, if you are interested in redoing, or you want to see the sources because you couldn't due to the small fonts, you can download them from my GitHub, or you can check up my website, or if you're interested in hardware, then you can check up my Twitter. I will post there if something new will come on the website. It's non-profit. So thank you very much for your attention. I will be happy to answer your questions. Yes, they are. Huawei, it's a very good example. Who has a Huawei phone? I'm naming them because it's not illegal to name them. You can just look for press articles about it. So you have Huawei is blocked in Germany. Huawei is blocked. They cannot participate in the contracts for critical infrastructure. There is a list of critical infrastructure components, telecommunication. So routers and selected switches, and they cannot participate due to the security reasons. Same happened with Huawei in the United States. Also, Germany has this initiative, Email Made in Germany, where they want the email, whenever there is communication sent within the country, not even one electron should cross the physical border of the country. So they would like to have all communication components within their own country. I would give also another example. Even in Czech Republic, they are right now producing own switches. They are open source, so you can take a look on them. You can buy them also on Amazon. and they are using some silicon chips from third-party manufacturers, so mainly from United States and from their fabs. But once they created the switch, they can easier detect, they know what's the functionality of the switch, and they can detect which components can be substituted, for instance, or filtered, must be filtered. So there are examples, things like this can happen. Yes, please. I really don't know. I haven't heard about it. I hope it is, because as you've seen, it's really hard to detect. If it's so small, like 3 lines of the VHDL code, then you could do, for instance, if you would like to find out if I have this Trojan, then you would the let's say most intuitive approach would be to do fuzzing, to go through all opcodes which you have in the Spark ISA, but then you would have to run it with all operands. So all operands, and plus it must not be that easy, because maybe it's a combination of commands which is triggering such a Trojan. So, in my opinion, it should be available, and I would say not having an electronic industry has also security consequences. Yes, please.
You mentioned the Trojans that take advantage of the different doping on silicon, essentially. So would it be practical, in your opinion, after, for example, decapping the chip, to affect like one NOR gate or any component on the chip itself, for example, to change the dopings somehow after like decapping the chip?
So you're saying we are reversing the chip, and then you would like to. The problem is, when you're reversing, you have those layers, so you will cut the layers. The chips are 3D right now, so then it's already damaged. You can only make a photo. If they are actually modifying the doping, then the point is the chip is damaged, because this inverter gate is not working properly. So you would probably detect it during the test phase. However, it's first of all convenient for them to say, this is a damaged chip. It happened in the fab. We don't know anything about it. We couldn't do anything, because it happens. Whenever you manufacture silicon on a wafer, this part of those wafer, the small chips, integrated circuits will be damaged by design, because you need an insane cleanness, you need clean rooms and so on, and because of this, you have this problem. I don't know if it answered your question.
Let's say we have the chip that already left the manufacturer.
Yeah. It will be extremely hard. I will say it's not true. You would destroy the chip. I would say extremely difficult. None. No, I would say I would rather it would be cheaper simply to produce a small series of chips as a manufacturer, couple of wafers which are already designed to be bad, and then just put if you ordered 100,000 of some controllers, then just put a small percentage, 5%, and then just count that maybe nobody will test it, or if they will test it, then maybe they will oversee it and so on. And then you are waiting under those products. You are waiting, they're on the market, people are changing in the companies, they are buying new keyboards, they are buying new memories, they are buying new processors. Then you are waiting, until they get a certain saturation point when they are through natural communication, let's say channels within the organization, within your company, and then you are conducting the attack. Yes, please. That's a very good question. So firstly, I have here for you a small summary. If you'd like to do it at home, you can do this, but it will be for the chips which are from 70s or 80s. Here is the cost of the equipment. You see like 300 for basic microscope used from 50. It's not that expensive. But as I said, it's working only for a very small and very old chips with a very high production process, but people are doing it. There's this excellent talk from Markus Janke and Peter Lackmann from CCC, House Computer Club Congress, about it, how to do this at home. FPGAs are proven to have also their own Trojans. So there are articles how to put it. In order to program FPGA, you need a controller, which is setting the values of the gates, which means that at this time, you can already program it. It's like in compilation, and very late, it's deployment of the image onto the FPGA, and you can still do this. So I would say that the easier thing to do is actually to produce own clean chips than to, even in very low technology, 1,500 for some simple purposes, than to try to reverse the existing chips and to check what's on them. Yes, please. Yeah. Yeah. You may try to damage them, but if you are producing, yes. So just the new chips are in very low process, so it's 7 nanometers right now. They are talking about it, or I don't know, 11, 17. They are very small. So even with this advanced stereo microscope, you won't see much. I've seen people which are trying to read from the SIM cards, which are way higher, and modify the memory values. So they try to get as IMSI codes directly with a probe. They are putting the probe directly to the cell memories. It's already very difficult and very expensive process, and it's very easy to destroy the chip. So I would say it's hardly improbable that people will try to modify the chip in post-production. I would say it's rather produced with this backdoor, or a certain small amount of the chips which you ordered, either not. I would. Yes, now I get your point. Yes, so for instance, there are chips which have some update possibility. A very famous example is a proven example. AMD have, for some small updates of ISA, when they see that their chip is not working properly, they left, or they made a test when they have microcoded functionality. So in microcode, also your assembly instruction, that the decoding is done based on some memory values in microcoded processor. So it's proven, there are publications that through those updates, so you can really design the chip so that you can modify it. However, it's very costly. So it's a costly. It decreases also the speed of the device. I would say in very sophisticated devices you could try to do this, but as I say, there are publications where they've proven that they can put through the microcode update, they can put a Trojan inside of it. So this is an example. They don't have to put the thermal and other factors on it. But if your chip is small and simple, then it makes no sense. I would say it's a lot of effort. It must be really, someone must really want to do this, and I would say it's an economical question rather than technical. But technically, it's possible. Okay. Thank you very much for the attention.